Hi everyone. Today we will look at runway orientation and number. So at the end of this topic, students should be able to understand the determination of runway orientation and number. Here we said relevance of meteorological studies on runway design. So here we said several factors in aerodrome design such as runway orientation, runway length, wake turbulence, visibility, and environmental issues are closely related with meteorology. Yes, because these are factors that can affect our flight or the taking off and landing of an aircraft. So under this section, we indicate the importance of meteorology in aviation, especially in airport design, rather than forecasting the weather for pilots and air traffic controllers. So our work is not to forecast weather for pilots or for aircraft to take off and land. No, the essence of it is to determine the best place to sight or to orientate our runway. So we need to consider these factors such as the length of the runway, wake turbulence, visibility, and environmental issues, which will affect the type of runway and our choice of runway as well as the location. It is important to note that a minor mistake could cause hazardous situations which may result in the death or damage financially. Crosswind components, fogginess and distribution and wind distribution, environmental management, obstacle and winter conditions should be analyzed before designing a new airport. In addition, all the observation data obtained from the nearest meteorological stations should also be examined in detail. So we need to consider crosswind components because they affect taking off and landing of aircraft. Then also the visibility, fogginess, and wind distribution. So the visibility at the airport is very important. That's why we're talking about fog or fogginess. Then we also need to talk about the distribution of wind. How does the wind blow around the airport within the time under study or consideration? The next thing we look at is International Civil Aviation Organization recommendation for runway and design, which is ICAO recommendations for runway design. The first thing we look at is crosswind. So under crosswind, which we mentioned earlier, the usability factor for the aerodrome is not less than 95%. However, where the prevailing wind and crosswind condition are not allowing to provide a percentage, the crosswind runway is required. So we're trying to say that when we're talking about usability factor of the aerodrome, it should not be less than 95%. But where we cannot avert such condition or we cannot provide for 95%, then we have to talk about we said the prevailing wind and the crosswind condition are not allowing to provide such a percentage, then we need to consider a crosswind runway. So that's what the ICAO states in 2009. So the data of the wind speed and direction, which is used for the calculation of the usability factor, should be as long period as possible, preferably not less than 5 years. So we shouldn't use any gathered data. That is to study the fogginess, the wind distribution, the wind speed. We need to also get data, meteorological data that is not less than 5 years. So it shouldn't be less than 5 years. So for parallel runways, where parallel non-instrument runways are intended for simultaneous use, the minimum distance between their center lines should be, according to International Civil Aviation Organization (ICAO) 2009, it says that 210 meters where higher code number is 3 or 4, 150 meters where the higher code number is between 2 and 120 meters where the higher code number is 1. Where parallel instrument runways are intended for simultaneous use. The minimum distance between their center or center line should be, according to ICAO recommendation 2009, it should be 1,035 meters for independent parallel approaches, 9,015 meters for dependent parallel approaches, 760 meters for independent parallel departures, and 760 meters for segregated parallel operations. So the when we're talking about parallel runways, these are runways that are orientated in a way that you orientate them in such a way they They run parallel to each other. We've looked at parallel runways already. The use of wind rose method in termination of the number and orientation of runway. This is also very important. So once we've gathered the wind data, it is important to now use the wind rules to determine the best place to sight the runway. The orientation of a runway is defined by the direction. So direction, we talk about direction relative to the magnetic north of the operation performed by the aircraft on the runway. Typically, but not always, runways are orientated in such a manner that they may be used in either direction. It is to orientate a runway in such a way that the operating in one direction is precluded, normally due to or nearby obstacles. So we try to orientate them in such a way that obstacle will not be a problem. So in addition to obstacle clearance consideration, runways are typically oriented based on the area wind condition. As such, an analysis of wind is essential for planning runways. As a general rule, the primary runway at the airport should be oriented as closely as practicable in the direction of the prevailing wind. When the landing and taking off aircraft are able to maneuver on a runway, as long as the wind component at right angle to the direction of travel, the crosswind component is not excessive. So what we are trying to say here is that if possible, the runway should be within the prevailing wind. It shouldn't be perpendicular to the prevailing the wind condition or crosswind condition. So that's why we call it crosswind. It shouldn't blow in a perpendicular direction, but along the line of takeoff or landing of the aircraft. The Federal Aviation Administration FAA recommends that the runway should be oriented so that aircraft may be landed at least 95% of the time. We less preferred to orient a runway in such a way that operating in one direction is precluded, normally due to nearby obstacle. When the wind coverage is less than 95%, a crosswind runway is recommended. We've said this already. Most times, the usability factor of the airport should be 95%. So if we cannot, we have to also have a crosswind runway. You have to build it along the crosswind. So, but in a way that it will not affect the takeoff and landing of the aircraft. So these are the things we look at. So the wind rules is the next thing we look at. The appropriate orientation of a runway at an airport can be determined through graphic vector analysis using a wind rules. A standard wind rules consists of a series of concentric cycles cut by radial line using polar coordinate graph paper. So we plot a wind rules. It has concentric cycles, and it also, let's look at it here. We have an example of a wind rules. You can see these are concentric cycles. Then these are the coordinates that we have. You can see north, north, northeast, 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 east, northeast. Here we have east, east, southeast, and so on and so forth. When you look at it, you'll be able to understand it. So this is the Windows coordinate system, and this is the template. We fix this template on the coordinate on the Windows and then rotate it, but by then we would have been able to plot the wind speed on these windows, so that the wind speed and direction, so that when we now put this template, we'll be able to determine the best place to orientate our runway. A typical wind rules popular coordinate system is shown on the diagram. You can see it here. This is the coordinate system. So here we're going to look at the shaded area that is in the next diagram. We'll look at where we have an example of what we're talking about, which is this. You can see it being rotated on a Windows. This is the template being rotated on the Windows. So the essence of all this here, let's look at the first of all the example, the wind data. So you can see the wind variable, the coordinate system that we have. Then this is through azimuth. That is the azimuth angle. They are all here. Then you can see the percentage time at which they are blowing, the wind speed range in miles per hour. So this is the time they blow within the the period of time, the year. So within this is the time they blow. You can see for this one, you can see the percentage time and then the wind speed. You can see 15 to 4 to 15, 15 to 20, 20 to 25, then 25 to 35. Then the percentage time this magnitude of winds are blowing. You can see it, they are all given here. So the total is given. You can see the total of the wind. When you sum this, it gives you this. Each of them gives you the total wind blowing. So here, what we now need to do is to plot it. We come back to here, you can see in the wind rows, we plot the magnitude of wind and the direction. After plotting it, just as what we have on the table here, you can see that what we have here for northeast, we have for the north, we have 24, 2.4, we have 0 0.4, 0 0.1. So we all have these things, they are all here. So for the north, you can see where we have it, the 4, and then 0 0.1, 0 0.4, 2.4. So, and here we have this for the north. The north northeast, let's see what we have from the table. The north northeast, from our table, let's look at what we have. North northeast, we have, you can see the 3.0, 1.2, 1.0. So let's go back. You see, for the north northeast, we have 3.0, which is the strongest. Then we have 1 point, the time duration. We have 1.2, 1.0, 0.5. You can see it. So we plot it like that. For the northeast, you go back, you can see northeast has 5.3, 1.6, 1.0, 0.4. So when we go back there, see the northeast 5.3. In the second case, we have the time it blows is at 1.6. This one is 1.0. This one is 0.4. So the time at which the wind blows on the table, as we have there, you see there is a percentage time is all given there. For each of it, we have the azimuth. We have for 4 to 15, 15 to 20. So these are the wind range or wind speed range, which is given in concentric cycle form. So you see the wind speed range for the first one, for the second one, for the third one, and for the fourth one. So once we've been able to plot all this, what is on the table, we go ahead and then bring that template which we have. The template is, it has the width of this template, or the total length of it is 30 miles per hour. So half of it is 15 miles per hour. Let's look at it here. You can see what we have here. You see half of it is 15 miles per hour. So we put it on these windows and rotate it. This template should be transparent in such a way that should be like a transparent ruler or transparent paper. So, or like a tracing paper. So you put it there and rotate it. The essence is to be able to, this template looks like a runway. That's why it is rectangular in form. So when you put it, you'll be able to determine while looking at it, just as we have here. Since we, after plotting this table, these windows from this table that we have here, so you see that we now bring in the template and put it. As we rotate the template, as we move it around, like you can see at this section, you check what is the magnitude of wind or that is covered by this. Let's say if we decide to put a runway here, let this template now be a runway and let this be the airport. So within this range now, what is the total wind, number of wind within this range? As we continue to rotate, we check which particular section of the airport has the highest wind concentration. So we check all the wind, magnitude of wind within this range and note it. Then we rotate it again and then note it until we're able to obtain the highest. You see, continue to rotate it. We rotate and until we get what we need. So here you can see, let's look at what they said here. We said, let's look at that example that we have here, example 3.1. He said, as an example, assume that the wind data for all conditions of visibility are shown on the table. I think we have already looked at the table. This wind data is plotted to scale as indicated above to obtain a wind rules shown in figure 3.2. So we use it to obtain a wind rules. You can see the wind rules that we have here. I've already shown you how it is being plotted on the table from the table to the windows. So this you start with these cycles. These are the concentric cycles showing the sector or the wind speed. Just as we have on the table, you see the first sector 4 to 15. This one is 15 to 20. This one is 20 to 25. Then this one is 25 to 30. So we enter the various values within the sector, just as we have here the first one, the second one, the third one, the fourth one. So you see that the strongest, the longest time is within this first one, then followed by the next one, and then followed by the third one, and then the fourth one. So the percentage of time the winds correspond to a given direction and the velocity range is marked in the proper sector of the wind rows by means of a polar coordinate for both wind direction and wind magnitude. The template is rotated about the center of the wind rows as explained earlier until the direction of the center line yields the maximum percentage of wind between the parallel lines. So once the optimum runway direction has been found in this manner, the next step is to read the bearing of the runway on the outer scale of the wind rows where the center line on the template crosses the wind direction scale. Because the true north is used for published wind data, this bearing usually will be different from that used in numbering runway since runway designations are based on magnetic bearing north. So we will have to adjust because we have the true north and we have the azimuth angle as well. So as illustrated in the figure 3.3, a one-way orientation on an azimuth to true north of 90 to 270, that is 2 bearing, will permit operation of 90.8% of time with the crosswind component not exceeding 15 miles per hour. That's why we use a template of 15, 30, and which the half of it is 15 miles per hour. Should the wind analysis not give the desired wind coverage, template may then be used to determine the direction of the second runway, which is a crosswind runway, which would increase the wind coverage to 95%. So what we're trying to say here is that after rotating this, we put it and rotate it to get the portion where we have the maximum wind. So if we are not able to, if the wind, the percentage of time covered here is not up to 95%, when we sum this, because remember from the table, we said this is the percentage of time the wind is blowing on the airport. So if we're able to sum all of them, it's not up to 95%, then we have to also rotate the runway, get another template and look for a crosswind runway. That is the second runway that will be able to assist this major runway because we must have 95% for the airport to be useful. If the usage of this runway is not up to 95, then we provide a supplementary runway, which is the crosswind runway. So that is all about runway orientation and number.